In this lesson, we will discuss literal equations. We're going to talk about what literal equations are. We're going to solve some literal equations and talk about why, and then we're going to go through a few examples. A literal equation is an equation where the variables represent known values. You'll maybe notice that literal sounds a lot like literary. They have the same root, which is lit, and you might think of like literature and the word literary, which all have to do with books that are made of letters. So literal equations are equations that are typically multivariable, and so they might have an x and a y or a pr and a t. Here are some examples of literal equations that you might come across in your studies. There's a lot of literal equations in science. There's literal equations in math and in finance. So the first example there, I equals PRT, that's the simple interest formula that you would use to figure out how much money your money is earning in a bank. The second one there is Ohm's law, which has to do with electricity. The third one there is the area of a rectangle, A equals LW. At the top of the second list there, we have F equals MA. That is the second law of motion, that force equals mass times acceleration. The one below that with the 9/5 is actually the Fahrenheit-Celsius equation to convert Celsius to Fahrenheit, and we're going to look at that one in a little more detail later. And the last one there is a mean arterial pressure, so it's something that a doctor or a nurse might look at, and the diastolic and the systolic has to do with your heartbeat and how much pressure is in your heart. And I don't know a whole lot about that particular formula, but I do know that it is something that you need in order to understand blood pressure. So those were some examples of literal equations that you might run across. When you're solving literal equations, it's very much like solving regular linear equations. If you compare the left and the right, on the left we have x plus 11 equals 18. We would subtract 11 from both sides, making it x equals 18 minus 11, so x equals 7. On the right side, we have a literal equation that has both x and y. If we're solving for x, we would just subtract y, just like we subtracted the 11. The big difference between literal equations and linear equations is that we're done with what's on the right. We're not trying to come up with an answer of like 7, like what you see on the left. We're just rearranging the letters so that it is solved for one of the letters. One of the letters is isolated on the right, all by itself, and everything else is on the right side of that equal sign. Whereas the equation on the left, I'm just trying to come up with an answer of 7. So that's the big difference between literal equations and linear equations, but the process is the same. You're still using the subtraction property of equality. You're still using multiplication and division properties of equality. You're still using distributive property. The methods, the steps are still the same. Just when you get down to your answer, it's going to look like this, like a formula, instead of an actual solution with a number. More on why you would need to do this. So this is an equation used to convert between Fahrenheit and Celsius. So here, it's actually set up to convert between Celsius into Fahrenheit, so that if you were given a Celsius temperature, you could use this formula to tell you what it would be in Fahrenheit. But if you solve it for C, then you can convert it from Fahrenheit into Celsius. And since we are students that are in the United States and we use Fahrenheit primarily, it would be really helpful if this formula was in terms of Fahrenheit so that we could convert to Celsius if we needed to. The steps are still the same. We still look for a least common multiple, which would be 5. So we're going to multiply everything by 5, and I'm going to use x even though I told you not to use x ever. So this would be 5f equals 9c plus, I'm going to use my calculator because I don't know that one off the top of my head, 160. And then we need to distribute, which we don't have that. We don't have any combined like terms. Switch sides, switch sides. Okay, so here's what you need to do. So if we're solving it for C, we're going to put a box around the terms that have C in it, and then we're going to circle all the terms that have anything other than C. So notice that has an F in it. And this has something other than C. So we're going to box all the terms that have C in it because we're solving for C. Just like when we solve for X, we would put a box around the terms that we were solving for X. So anything that's not C is going to switch sides so that it's on the other side. So I need to move the 160 over with the 5F. And the way that I do that, that's a plus. So I'm going to subtract it over here. And that way, now everything that's not C is on the same side, and everything that is C is on the same side of the equal sign. So we switch sides, combine again. This time we can't combine these two together because they're not like terms, so we don't really need that step. And then we divide by the number that's with the variable that we're solving for. So we're solving for C, so we're going to divide this whole thing by 9. And I'm going to go ahead and distribute that to each term. So I get 5/9 F minus 160 divided by 9. Does not go in nicely. So I'm going to leave it as 160 divided by 9 equals C. Now, the real formula is you would factor out 5/9, and then you'd have F minus whatever that is, 32, I think. But we're going to leave it like this because it's solved for C and that's what it asks to do. So now if I had Fahrenheit temperatures and I was trying to convert to Celsius, I could just plug in those Fahrenheit numbers right here and then calculate 5/9 times my Fahrenheit minus 160 divided by 9, and that would give me my Celsius. And that's why it's important to be able to solve literal equations, is because this form is a lot more useful to me because all of my temperatures would be in Fahrenheit than this form is. And so by manipulating the equations, you can put them in a form that's more useful. Let's look at some more examples. Amelia says the formula S equals 2 pi RH is equivalent to R equals S over 2 pi H. Are they correct? Taking a look at this, Amelia solved the S equals 2 pi RH for R. See that right there? So let's try to solve this for R and see if we can catch any of Amelia's mistakes. First, we're going to look for a least common multiple, and again, we're solving for R because we want to see if this is the same as this. So first we look for a least common multiple. There's no fractions, so we don't need to do that step. There's no distributing. There's nothing to combine. Switch sides, switch sides. Okay, so if we're solving for R, we're going to put a box around the term that has R in it and a circle around everything else. And the reason why I put the box around this whole thing is there's no plus or minus in this, so this whole thing is a term. And they're already separated. The circles are on the left side and the boxes are on the right side. They're already separated. So there's nothing to combine again. So we're all the way down to divide. That's all we have to do is divide by everything that is not R. Divide by everything that is not R. So I'm going to divide by 2. I'm going to divide by pi. I'm going to divide by H. And that's going to get rid of the 2 pi and the H and leave me with just R on this side. Because this is all multiplications. The way that I get rid of it is by dividing. And that leaves me with just R on this side. Is this equivalent to this? It sure is. So they are correct. Yes. Let's take a look at one more example. Cole says that the formula P equals FG over 3 is equivalent to G equals P plus 3 over F. Are they correct? Now, right away, I see a red flag with Cole because there are 2 terms in this one, and there's no pluses over here. So it seems really unlikely to me that these are actually equivalent. If this one has a plus, then this one is probably going to have a minus. If this one has a minus, then this one has a plus. If this one doesn't have a plus or a minus, this one probably won't have a plus or a minus either. So I'm thinking that Cole may be incorrect, but let's just walk through the steps anyway. This one is solved for G, so let's solve Cole's formula for G. So we're solving for G. Least common multiple, there is one here, so I'm going to multiply both sides by 3 to get rid of that denominator. Don't need to distribute. I don't have anything to combine. Let's check our switch sides. So we're solving for g, so I'm going to put a box around this whole thing because these are not terms. So this is my g term, and this is everything that's not g, and I don't have anything else that's not g, and they're already separated. So we don't need that one, and then we don't need that one, because if you need this one, then you need this one, but if you don't need this one, you don't need this one. Okay, and then we're on to divide. We're going to divide by everything that's not g on that side with the g in order to get g by himself. He's a loner. He likes to be all by his lonesome. And this would be solved for g. 3p over f equals g. This is p plus 3. Is that the same thing, 3p and p plus 3? Is that the same thing? It's just in a different order? No, it's not the same thing. We know it's not the same thing because this is p plus 3 and this is 3 times p, and that's two different operations. So I'm sorry, Cole, they are not, this is not correct.